Well, thank you. Welcome. On behalf of Carnegie Science, our new president, John Mulcahy, I'd like to welcome you to this wonderful evening where we're going to have a spectacular conversation between 2024 Kavli Laureate, David Charbonneau, and journalist Frank Senso. So this is something that Carnegie Science has been putting on for some time. Carnegie Science was actually created by Andrew Carnegie in 1902 as the Carnegie Institution of Washington, as something brand new, a private independent research organization, which has done some amazing things over the years, ever since its founding. At present incarnation, it has three different divisions. Here in Washington, D.C. is the Earth and Planetary Lab up in Chevy Chase, where I'm a member for the last 44 years, actually. Have not been able to get rid of me. There's also the Carnegie Observatories in Pasadena, which also runs the Las Camanas Observatory, where we have literally our own mountaintop in Chile and one of the best observing sites in the world. And then the third division is the Biosphere Engineering Division, which is being set up right now. It's in the process of being created in Pasadena. Now, Carnegie Science is proud to be collaborating tonight with three entities: the Kavli Foundation, of course, which awards the Kavli Prize. We're also collaborating with the Norwegian Ministry of Education and Research, and also with, let's see, the, sorry. Look at my cheat sheet for that one. We had to change the last minute. I don't want to get it wrong. The cheat sheet is the Norwegian Academy of Science and Letters. In fact, that's a really bad blopper, because we're about to hear now from if we have the videos about you ready to go on, from Annalyn Eriksson, who is going to be, she's the president of the Norwegian Academy of Science and Letters, and we'll be hearing from her right now. Tell us a little bit more about how the Kavli Prize is awarded.
My name is Annalyn Eriksson, and I am the president of the Norwegian Academy of Science and Letters in Oslo. I am sorry for not being with you at Carnegie today. It is a great honor for our academy to cooperate with the Kavli Foundation and the Carnegie Institution for Science. We also appreciate the support of the Norwegian Embassy in Washington, D.C. for today's event, where Kavli Prize Laureate David Charbonneau from Harvard University, Canada and USA will give his lecture. Professor Charbonneau received the Kavli Prize in Astrophysics in 2024, together with Sarah Seeger, MIT, for their groundbreaking work on the discovery and characterization of extrasolar planets and their atmospheres. When the Kavli Prize is awarded, we are so privileged to have His Majesty King Harold V awarding the prize to the laureates. Fred Kavli's vision for the Kavli Prize is the recognition of outstanding scientific research in the fields of nanoscience, neuroscience, and astrophysics. Kavli wanted to honor highly creative scientists, promote public understanding of scientists and their work, and foster international cooperation among scientists. This event is an invaluable contribution to communicate the great achievements of the Kavli Prize laureates. The Kavli Prize was established in 2005 between the Kavli Foundation, the Norwegian Ministry of Education and Research, and the Norwegian Academy of Science and Letters. This cooperation is the key to the international standing of the Kavli Prize. Each of the three Kavli Prizes, Astrophysics, Nanoscience, and Neuroscience, have a prize committee appointed by our academy. The high reputation of the Kavli Prize is due to the solid work by the prize committees. The members of the committees are world-leading scientists within their respective fields, and they are chosen by the Royal Society, the French Academy of Sciences, the Max Planck Society, the National Academy of Sciences in the US, and the Chinese Academy of Sciences. Professor David Charbonneau is the Fred Kavli Professor of Astrophysics at Harvard University. Charbonneau pioneered the application of space-based observatories to perform the first studies of the atmospheres of giant extrasolar planets. He used the Hubble Space Telescope to find evidence for sodium around the giant planet's atmosphere. Currently, he is leading the innovative M-Earth project aiming to detect rocky planets. I am looking forward to listening to the lecture from today's guest of honor, David Charbonneau, and wish you all an inspiring evening. Thank you.
Okay, very good. Now let me introduce our speaker for the evening, David Charbonneau. As Dr. Erickson just noted, Fred Kavli, professor of astrophysics at Harvard, is David Charbonneau. David did his undergraduate work at the University of Toronto, getting a Bachelor of Science degree. He then went on to Harvard University to get his PhD. He spent a couple of years out at Caltech as a Robert Mulliken Fellow, then returned back to Harvard because I guess he decided he liked snow and ice more than surf and sun. David has won a number of prizes. I won't try to list them all for you, but he is a member of the National Academy of Sciences and of the American Academy of Arts and Sciences. Today he's being honored for his sharing the 2024 Kavli Prize in Astrophysics with Sarah Seeger, who I'm happy to say was a colleague of mine at Carnegie for 5 years. She had the office right next to me. I was able to enjoy her input on the developing field of extrasolar planets. So the two of them have won the prize together in 2024 for their work on characterizing and detection of atmospheres around exoplanets. So let me back up a little bit to say, why are exoplanets a new field of research? It's a new field that just began literally 30 years ago. In the summer of 1995, astronomers came up with the first definite evidence of a planetary body in orbit around a sun-like star. And for that discovery, the two Swiss astronomers, Michel Mayor and Didier Queloz, won the Nobel Prize in 2019. So the interesting thing is that these were hot Jupiters, because this first one that was found around a star called 51 Peg, a solar type star, had roughly half the mass of Jupiter on a nice circular orbit, much like our Jupiter is. But the strange thing was the orbital period was not 12 years like Jupiter, it was 4.23 days. That means it's very close. And that also means it's therefore going to be very hot. It's 100 times closer to a star than Jupiter is. So it literally is a hot Jupiter. So over the next 5 years, people are doing radial velocity searches, like my colleague at Carnegie, Paul Butler, found a total of 10 hot Jupiters in total. The significance of that is that when you have 10 hot Jupiters, which are roughly 1/10 the size of their star, orbiting very close to their host star, 1 out of 10 of them should be transiting. That is, its orbit should pass in front of the star, periodically blocking the light. And you want to see if that's actually happening or not, because that would be the idea to merely confirm that the radial velocity detections were correct. It gives you a second independent way of checking to see if that's really what you think is true. So in 2000, there was a 10th planet found around HD 209458b by the radial velocity folks. And so several teams worldwide began trying to see if finally this 10th one's going to transit or not, or see if maybe radial velocity spectroscopy is just being fooled by some spurious signals. Well, David was by then a graduate student at Harvard. His advisor, Robert Noyes, sent him out to work with Tim Brown out of the High Altitude Observatory in Boulder, Colorado. And Tim Brown had a homemade 4-inch telescope he stored in a shed out in the parking lot at NCAR up in the hills to the south of, up in the hills south of Boulder. And so for a couple of nights in 2000, Dave went out and took measurements of the brightness of the star. And after a couple of cycles of 4.23 days, he finally had enough dips that he said, this is real. And Tim Brown agreed, and they went and rushed to print. And this was published along with a competing claim. My colleague Paul Butler was involved with another team, but they both essentially found around the same star, the same dips, which confirmed that, by golly, this hot Jupiter really was there. So it's a brand new birth for the field, and David deserves credit for having been one discovering something brand new. But that's not the only thing he discovered brand new. Knowing that he now had a hot Jupiter around HD 209458b, the next year he used Hubble Space Telescope to follow the star while the planet's passing in front of the star during the transit. And he noticed that there was a signature of the star's light passing through the atmosphere of the planet that revealed the presence of sodium escaping from this hot surface. And so again, for the first time, he was able to detect an atmospheric element in an extrasolar planet. So that's the second first in a row. And not to be stopping there, a couple of years later in 2005, he was this time studying not HD 29458b, but instead traced one, another hot Jupiter. And he followed this with a Spitzer Space Telescope, and for the first time detected thermal emission from the planet as passing behind the star. Subtract the starlight with star and planet are there. Planet disappears. Subtract the two, you get the planet's light. First time was thermal emission was detected from an extrasolar planet. So for all of these reasons and more that you'll hear about tonight, David certainly deserves the Kavli Prize. To move on to our moderator tonight, Frank Sesno, we're happy to have with us. He's done a number of these lectures in the past. He's currently a professor at George Washington University, and he's director of the Institute for Strategic Studies in the School of Media and Public Policy. He also spent 20 years at CNN, where he was a Washington bureau chief, White House correspondent, and an anchor. And for that work, he earned an Emmy. So at this point, I want to welcome both David and Frank to the stage and prepare us for a fascinating evening where hopefully we'll not be checking and worrying about what our 401k accounts are.
Well, thank you very much. The good news is no one's going to have to check their 401k because they've already done it. So not much going. Well, welcome and thank you for being with us.
It's really exciting to be here.
It's a great time to have you in Washington, D.C., I guess. So speaking of outer space, but we were chatting and we thought we might actually start by asking you a few questions. How many people in the audience think there is life beyond planet Earth? Raise your hand. Wow. How many of you think we will detect life within what period of time?
A decade.
A decade. That we will detect life within a decade.
I'm looking at my NASA colleagues.
How many people in the audience think we've already detected life? How'd they do?
Well, we don't know the answer to some of those questions. So.
Well, where's your vote?
Okay, so very interesting. So we now know the universe is infinite. So it's not unreasonable to think there's life out there. But the real question is life sufficiently common that it's around a close enough star that we can actually study it, learn about, is it multicellular? Is it an animal? What is it? And that's a much smaller set of stars. And that we truly don't know. Because it can't just be a 1 in a trillion thing. It has to be sort of a 10% of the time that you have a planet, you get life. And that's what's exciting to me.
But you're sort of staring out there on a regular basis, right?
Absolutely.
Yeah.
But the question is, we want to find the actual abodes for life and actually find planets where we can study them in detail and really see if there is life, and not just this mathematical argument that there's so many stars and there's so many galaxies that surely there's life out there. I don't find that very. I'm an observer. I want the data.
Okay, well, we're going to talk about what you observe and some of the data. I do want to invite all of you. If you've seen the QR code, you can put your questions into the app, and I will be looking at those, and we'll engage those as we go. But let's start. So you look at atmospheres, right? And you study atmospheres, and you look for what's in those atmospheres to tell us what we think we know and what we can see and what we can detect. How do these exoplanets produce atmospheres?
Yeah.
And do atmospheres, do exoplanets keep their atmospheres, lose their atmospheres?
Right.
Is it a dynamic process?
Yes. All right. Can I'm going to see if we can go to
pictures are good.
So these are the kinds of planets that we really, I think, are going to focus on tonight. And these are the terrestrial planets of the solar system. Okay, so that's Mercury, Venus, Earth, Mars, drawn correctly to scale. And what's so fascinating, of course, is some of them have Mercury has no atmosphere. Mars is a very tenuous atmosphere. Venus has a tremendous atmosphere, much thicker atmosphere than the Earth. And why is it that the Earth has the atmosphere it does? Why did Mercury and mostly Mars lose their atmospheres? And that's, I think, a question that's hard to answer when you only have 4 planets. But if we could find hundreds of planets around other stars, we could really figure out the answer and put the solar system in context.
So what does that tell us when we can determine how they keep them, whether they lose them?
Yeah, so we think that planets, after they form, they're very hot, and the gases that will make the atmosphere are locked in the rocks, and then they are outgassed through volcanoes. And then if the planet has a high enough gravity, it can keep the atmosphere, and if it has a low gravity, the atmosphere is lost to space. But the other big factor is the behavior of the star. Some stars are good parents. They're calm, they have nice household, you know, and the planets get to keep their atmospheres. Some stars might blast away the atmospheres of planets that otherwise could have been good abodes.
But you can see that too.
That's what we're so excited about. This is all happening right now. We are using telescopes on the ground in space to actually see. There are planets we know of where we can not just see that they have atmospheres, but we can see they're actively losing their atmospheres because of the star.
So when we're looking for that, and when you're looking for life outside of our solar system, right? Is that, can we do that from spaceships? Do we do that with, I mean, talk to us about that.
Yeah, right. So you know, I assume you're all here in part because you're interested to know how we're actually going to go and do this experiment. And so I have a slide that's, I think, evocative here. Okay, all right. So there's, you know, how are you going to go find life on other planets, right? So one idea is spaceships. Let's build spaceships. We're going to get on spaceships, or we're going to send robots, and they're going to go directly find the life. It sounds good, right? And I'm a big science fiction fan. The trouble is, if you take the fastest spacecraft we've ever built and you pointed it directly at the closest star other than the sun, it would take 100,000 years to get there. So the idea is a good theoretical idea, but in practice, it doesn't work. Here's another idea, okay? How many recognize, put your hand up if you recognize the movie that this is from, right? This is Contact. And it's about an idealistic young astronomer, graduate student, who has a mean advisor. Advisor's always trying to steal credit for her discoveries.
I would take a great creative license with that. That doesn't exist, right?
And of course, you know, she's interested in signals being broadcast from other civilizations. And I think that's a fascinating idea, but the trouble is that's a very, if you begin to think about that question, right, you want not just life, but intelligent life. You want life that's interested in radio telescopes. It has to also want to have its presence known. It has to be interested in communicating. And there's all sorts of life on the Earth that doesn't do any of that. I mean, whales don't seem to be very interested in building radio telescopes, but we'd like to know if there's organisms like that. So that's why I think the other approach, the big idea, is not spaceships. It's not SETI. It's not listening.
Right.
It's actually realizing that if you look at the Earth, I don't know if I can go back here. The Earth is different from afar. From space, you can see it's different. Okay, the continents are green instead of brown. Okay, the atmosphere has the second most abundant gas in the atmosphere is oxygen, which is produced by life. So unintentional, life has no intent of communicating its presence, but it's changed the appearance of the planet in a way that you could see across the light years.
I want you to talk about that a little bit more too, that life creates oxygen, because I think a lot of people would think it's the other way around.
Oh yeah, no, so we consume oxygen, but there was life that first created all that oxygen so that we could have these more complicated multicellular beings like ourselves. And so, you know, the fundamental source of energy, if you're on the surface of a planet, is the light falling on the planet. And so basic organisms, simple organisms on the Earth began to do photosynthesis to use that radiant energy, and they produced as a waste product is oxygen. So all the oxygen in the atmosphere, of course, that was all produced by the unintentional. It's the waste product of a dominant form of life that was present for billions of years. That's the signal we're trying to see from space.
So if oxygen is the second most abundant molecule in the atmosphere, how are you trying to find that in brown places like that, right? How are you trying to detect these?
Yeah, right. So, okay, let's go. I think this is the next one here. Okay, so here's the idea. Okay, so we would love to be able to just take a picture. We'd love to be able to take a picture. You could build a really nice telescope and you take a picture of the star and the planets next to it, and then you just simply go and study that planet. And that's a great idea, and we are on that idea, and NASA is working very hard on that idea. That idea for planets like the Earth, that idea is 10 or 15 or 20 years away. Okay, it requires incredible technology development. And so the path we're using now is to instead wait for the planet to pass in front of the star. And then when it passes in front of the star is now a flashlight. It is backlighting the atmosphere. And so the light from the star passes through the atmosphere, and you catch that with your telescope. and then encoded on that light, just during moments when the planet's in front of the star, is the fingerprint of whatever atoms or molecules are in the atmosphere. And so it isn't just oxygen, it's water, it's methane, it's carbon dioxide, it's carbon monoxide, it's whatever is in that atmosphere. And the facilities we want to use, right? So we have the James Webb Space Telescope, incredibly powerful space-based observatory. It's sensitive to infrared light, which is where most molecules are responsive. And then on the ground, we're trying to build these very large observatories. So that exists. That's been kicking butt in space for years, several years now. This idea, this is the Giant Magellan Telescope. We want to build very big telescopes that are so big you could never launch them in space. Okay, because they're too massive. And just for scale, like each of the mirrors on that guy are bigger than the entire mirror here. Okay, so this is a tremendously large observatory. Okay, but we haven't built that yet. But from the ground, then it could go and study various molecules in the atmosphere too. So that's the idea. This is the idea of how I think we can really go and look now for life on other planets.
So where will something like Magellan take us? What will that allow us to see that we can't see now, to detect what we can't detect now?
Oh, so it has to do, they're very complementary. So James Webb is very sensitive to infrared radiation, okay? And there's certain molecules that display, you know, their fingerprint is in the infrared, okay? So water, that absorbs lots of infrared light, carbon dioxide, lots of infrared light, methane, okay? Oxygen, as it turns out, it's the transitions of oxygen, the wavelengths of light that oxygen absorbs are not predominantly in the infrared. They're in the optical and visible light that we can see. And that's, and it's also, it is a much more subtle signal. And so you need a bigger telescope, but you can do it from the ground. You don't have to do it from space. If you want to conclude that a planet has life, you need to detect you can't just detect oxygen. You have to detect 10 different molecules, and together they tell that story. And so some of those molecules I think will be detected with James Webb, and some I think will be detected from the ground with telescopes like the GMT.
What's an M dwarf?
Oh, okay.
Who's heard of an M dwarf? Lots have not.
Okay, so an M dwarf is just a small star. Okay, and
now you have.
Right. And so the reason that we're interested in M dwarfs is that this idea doesn't work for sun-like stars. Okay, it doesn't work for sun-like stars because sun-like stars are really big. Okay, so when I was in high school, I was told a big lie, which is the sun is an average star. The sun is not an average star. Most stars in the universe are much, much smaller. They're about 10 or 20% the size of the sun, the mass of the sun, and they put out 1/1000th the amount of light that the sun puts out. So the galaxy is full of these tiny stars called M dwarfs. And I'm going to show an image here, which might be recognizable to some of you, which basically shows that to scale. So there's the sun, okay, on the left, and the Earth drawn to scale. And the reason that this transit idea doesn't work is because the size, that little onion skin of an atmosphere, it simply is too small a signal compared to the star to be able to actually measure it with the telescopes that we have, with James Webb and even with those bigger ground-based telescopes. But if I can shrink the star, then the size of the atmosphere compared to the size of the star becomes detectable. And so because the galaxy is mostly full of these M dwarfs, okay, so these are the guys we're talking about here. We call them M4s, M6s, okay? And that just has to do with how big they are. They're now small enough that if we catch an Earth-like planet in front of them, we can, a 6.5-meter telescope in space, the James Webb Space Telescope is big enough to go and tell us whether there's an atmosphere. So it's a strategic opportunity. It's an opportunity that nature has provided us, in part because M dwarfs are really good at making terrestrial planets that are made of rock and iron and are similar in size to Venus and the Earth.
And there are infinite numbers of M dwarfs. Are any of them, no. How do I use this term advisedly? Close by?
Yes. So they outnumber us 12 to 1. Okay, so there's 12 times more M dwarfs than there are sun-like stars in the galaxy. Okay, now the sun-like stars, we also want to pursue that idea because that's the one case where we know that you got planets with life. So it'd be foolish not to pursue that. But in the here and now, the thing we can do now is pursue this idea: do these stars have planets? Do they have planets that are the same temperature and size as the Earth, and do those planets have atmospheres? And that is what many of my colleagues around the world are pursuing, okay? And so what we've learned is that, yes, all of these M dwarfs make planets that are the same size as the Earth, these terrestrial type planets. Sometimes they're hotter, sometimes they're cooler. And the specific idea that we're pursuing right now is, do we actually have evidence that those planets have kept their atmospheres?
So you're the principal investigator of the M-Earth project, right?
Yeah.
And that's located in Arizona and in Chile, scanning the skies every night, looking for these guys.
Yeah.
What are you looking for? What are you seeing? What are we seeing through these things?
Yeah, so this, in terms of all the projects that I've engaged in, just to share a bit about my job, right? So a great part of my job is I work with young scientists who I am pretty sure are smarter and faster than me. And I get to collaborate with them on these small projects. So I also participate in the big projects, okay? But this is a small project. This was like me, a really great postdoc, a couple graduate students. But basically, there's an array of telescopes in Arizona, and there's 8 telescopes, and each telescope, the mirror is only about this big. Okay, so those are pretty small. Those are like large. I mean, they're very high quality mirrors, but in terms of size, they're not that different from what a high-end amateur might have. And then we have 8 more in Chile. And we have this list of all the nearby M dwarfs. Okay, so the closest, if you draw a bubble around the Earth, and you make the bubble really small. So let's say we go out to like 50 light years. Okay, so if you're not an astronomer, like that sounds really far. But for me, that's the local neighborhood. Okay, so for scale, if I took the galaxy, I took the entire galaxy and I shrink it down to the size of the United States.
Mm-hmm.
Okay,
Mm-hmm.
we're now talking about studying stars that are within Central Park in New York.
Wow.
So it's just a tiny part of the galaxy, because we want to study stars that are close, because we can now get more light from them and learn about their planets. Okay, and yet within that volume of space, there are about 500 of these M dwarfs, and that's what MIRF is doing. So it's looking every single night. It looks at this star, this star, and then goes back and repeats it, because we don't want to miss one of these planets passing in front of its star. So this project basically has found a lot of the terrestrial planets, rocky planets orbiting the closest stars. And then we hand those off to the James Webb Space Telescope, where we can then go and see if they have atmospheres. So this is the discovery system. And then the characterization system are these bigger telescopes.
And you're also part of the NASA test mission as
right.
well.
Yeah. So then
so what's the relationship, and what is that, and how's that tie into this one?
Yeah. This is the kind of complementary idea. Okay. So we've been running MIRF on the ground for about 12 years. But then I was also I'm a co-investigator on the TESS mission, and TESS is doing the same idea, but from space. Now the trick is the telescopes are much smaller, actually. Okay, so if you look at the TESS mission, you can see those 4 camera lenses. Those are the telescopes. Okay, the camera lenses are only about this big on TESS. So if you're into high-end photography, you might have a lens that's actually as big as these lenses. Okay. But TESS is the same idea. TESS is basically takes these 4 lenses and it takes a snapshot of the heavens, and it does that continuously for 28 days. And then it moves over and monitors another set of stars for 28 days and another set of stars for 28 days. And so it's not selectively looking for all the nearby M dwarfs, but because it will eventually do the whole sky, it is also looking at those, and also it's a discovery mission. So MIRF does it from the ground. MIRF can look over much longer timescales, and we can also point MIRF. TESS has to kind of follow this pattern, but it gets incredible. The best place to put a telescope is you can't beat space. There's no clouds in space. It's never rainy in space.
Right.
Yeah.
Lights aren't on in the neighbor's house.
Lights are not on. The only danger is typically telescopes are smaller in space because of weight concerns.
Yeah.
But together, MIRF and projects like MIRF and TESS have now found of order 100 of these sort of rocky, I wouldn't say Earth-like, because some of them are much hotter and some are much colder, but terrestrial planets around nearby stars. So we have this population of planets. So the question was, do these nearby stars make such planets? We now have firmly answered, they make them in incredible numbers. And now the question is, okay, are these really siblings of the Earth and Venus, or are these actually very, very different things? Are they sort of like handshaking third cousins that look outwardly like the Earth, but actually are completely different when you drill
When
down?
you say they make these in huge numbers,
Yes.
what are we talking about here? What do these solar systems look like? Or I mean, how many exoplanets are rotating around, orbiting their suns?
Yeah, so we believe, based on data from these various projects, that when you do the statistics, basically all stars make planets. So we now understand that planet formation is a natural consequence of star formation. If you make a star, you will naturally have a disk of material left over. This idea, this goes back to Kant, okay? So Immanuel Kant, who you think of as a philosopher, noticed that all the planets in the solar system orbit in the same direction, and they all spin in the same direction that they orbit, with a few exceptions. And so he thought, well, they must form in a disk. We now, centuries later, we have the direct evidence that, yes, you do see these systems of planets in great numbers. So the bottom line is all of these stars make such planets.
Mhm.
M dwarfs are particularly good at making systems of these rocky planets. And also, it looks like the typical size of those small rocky planets is sort of Earth-sized.
So that's what I wanted to ask you. Alan was talking before about hot Jupiters.
Right.
So do we have Jupiters around these small stars? And
Yeah.
what does that tell us?
Yeah. Okay. So in the solar system, so Alan was talking about hot Jupiters.
Hot Jupiter.
And those are Jupiters that formed far away from their stars and they moved in. And that would be catastrophic for Earth-like planets because we are just a tiny pipsqueak. Okay, the Earth is 1/300th the mass of Jupiter. So if Jupiter were to come barreling in, it'd be curtains for the Earth. The Earth would be thrown out into space. Okay, but the very interesting question is, in the solar system, what was the role of Jupiter and Saturn? And Jupiter and Saturn had an enormous role in the solar system. So if I show these images here, okay, so this planet here, this circle right here, what is that guy? Who is that in the solar system? This one over here.
I hear somebody over here.
Mercury, right? And often when I show this, people say, you're very perceptive. Many people say, oh, it's the moon. The moon and Mercury, and to some extent Mars, they all are covered in craters. Okay, so it's this huge clue about something really important that happened early in the solar system. And we now understand that when Jupiter and Saturn were formed, okay, there was all this leftover material in the outer solar system. So think about, you build these giant buildings, that's Jupiter and Saturn, and then you have all these cinder blocks left over, okay? And then what Jupiter and Saturn did is, after they formed, their gravity, because they migrated a bit, their gravity was so powerful, it cast all of that material down and rained down upon the early terrestrial planets. So the Earth and Venus and Mars and Mercury, they were all bombarded with these objects. Now, the Earth has erased that information because the Earth has active plate tectonics. So there's lava and that information goes away. But for things that are inactive, like Mercury, we can see that direct. Okay, so we think that perhaps a lot of the oceans were made by this material.
Mm-hmm.
A lot of the material that would then go on to form the atmospheres of planets would be influenced by this material. So the reason I'm telling you all this is because what we've discovered for all of these planets orbiting nearby M dwarfs is that although the planets make large numbers, the stars make incredible numbers of terrestrial planets, they don't appear to make Jupiters ever. There are no Jupiters around these low mass stars. And so that's what makes me think, oh gosh, maybe these planets outwardly appear like the Earth and Venus, but they didn't get that inventory, that chemical inventory of material that was thrown in from the outer solar system. So maybe they don't have oceans, or maybe their oceans are very different, or maybe the initial compositions of their atmospheres are very different because they didn't go through this epoch. By the way, in the solar system, we call this the late heavy bombardment. Late meaning it happened after the formation of the solar system, and heavy bombardment is pretty self-explanatory. That's when all this stuff came raining in.
So you're really scrutinizing these worlds, right, to see if they have atmospheres.
Yes.
We've detected a number of things, X-rays and flares and all kinds of things that they're emitting. What do you think about these worlds and their atmosphere? What do we know about them?
Right. So the first order question, and like this is really the here and now of this field, is 5 years ago, if I had given this talk, it would be, do these planets exist? Can we find these planets? Gosh, there's this big opportunity because the galaxy is full of small stars that are nearby. we've answered that. Now the question is, okay, do these planets actually have atmospheres or not? Are they all Mercuries or are they all Venuses? Okay, so how are we going to answer that question? Okay, so I want to start with this picture over here. So this idea is, when the stars are active, when the stars are young, okay, they're going to go and they're going to sandblast their planets, and the planet, it's a competition. So the Earth is losing atmosphere all the time, but it's very slow, and the Earth replenishes its atmosphere through volcanism. Okay, so the Earth is in kind of an equilibrium. But you can imagine if you had a star that was much more active, it produced a lot more X-rays and ultraviolet light and flares, and the gravity of the planet was a bit lower, then you would get to a point where there's no atmosphere. Okay, you just lose it completely. But I'm not interested in theory. I like theories. Okay, I'm actually reading all the short stories of Sherlock Holmes right now, and there's so many zingers in there about evidence and data. And one of the things that we hear a lot is that it is a capital offense to theorize before you have data. That you shouldn't just go out and
Could you
theorize.
spread that around Washington a little bit? We could use some of that.
You must first, you just look and you observe and you look for patterns and you
Which
get
is
data.
what you're doing.
And then you start to put together theories, and that we must be very suspicious of theories before we have all the data. Okay, so how do we actually answer this question observationally? And the idea is this observation here. So this observation was completed by an astronomer named Laura Kreidberg, and I was on the team with Laura. I was actually an advisor. She was a postdoc, and she said, okay, I want to get a whole bunch of time on the Spitzer Space Telescope, which was the preeminent infrared observatory at the time. This was before the James Webb. And the idea was the following. Okay, so you have the star, and the planet is going around the star. The planet is close enough that it's tidally locked. Okay, it's always going to present the same face to the star. And so that means that at some points you're looking at the night side of the planet, right? The planet is pointed towards the star, but you're looking at the backside. Okay, and then it swings around this way, and now you're looking at the day side of the planet. Okay, so if you're on the planet, you can see the star, and now we can see the infrared radiation from the day side and the night side. Okay, so if there's an atmosphere, then the temperature on the day side and the night side should not be that different. Okay, so when we all finish here tonight, the sun will have set in Washington, D.C. It will not be 0 Kelvin, okay? It'll be a little bit cooler than it was during the beautiful day today, but basically the temperature at night and during the day is the same. If there's no atmosphere, the moment the sun goes below the horizon, the planet quickly becomes ice cold. We see that, like the dark side of Mercury is ice cold. Okay, so what did Laura find, right? So what she measured was as the planet goes around its star, you see it goes from being very bright in the infrared, that's the peak, to basically having no emission in the infrared. So there's a really hot day side and an ice cold night side, ergo there's no atmosphere. So this idea is now, I would say it's the most exciting thing that we're doing with the, okay, my opinion, with the James Webb Space Telescope and trying to do with other observatories, picking up now all of these rocky planets that we know about and really asking, as we get to colder and colder planets that are farther from their star, so really hot planets, like we were not surprised, right? This planet should not have held onto its atmosphere because it was so close to its star. But as we get to slightly cooler ones, are we going to see a point where all of a sudden they do have atmospheres? And so we call that idea the cosmic shoreline, where now we find the planets that are massive enough and cold enough that they've kept their atmospheres. And then the next question will be, okay, what's the atmosphere made of? Can we see oxygen?
Alan spoke about all the firsts that you've done, and I love asking this question of the scientists that I talk to here and elsewhere, which is, what is your aha moment? What is something that you discovered that, like you said, oh my God, look at this, or that just excited you beyond belief? Because there's so much here, and it's moved so quickly. You talk about what we learned in just the last 5 years, right? I mean, when you started this, there were no exoplanets,
right?
Or there were exoplanets we didn't know about,
right? So I am really blessed in that I've had a bunch of those moments, and I recognize that I'm very fortunate to have felt that as a scientist. I would say that it's not what you think, you know, that when you're the first to see something, I think in movies or in books, you think, okay, you know, eureka, there it is, I've solved it. I'm the first to see this, but actually it's not that way. It's actually a very uncomfortable moment because you really worry, like, is this really happening? I want to go and discover things and I see a signal. Am I deluding myself?
Yeah.
Am I convincing myself that there's more there? And we, even in the exoplanet community, we have nicknames for this behavior where people basically have a fever, they're delusional. They see something that will not later be confirmed by colleagues. In terms of specific moments, there's no question, as a what, 22-year-old using a 4-inch telescope in a parking lot in Boulder, Colorado, and analyzing those data and being the first to see a transit, and then checking nights when there wouldn't have been an event and then they were flat, and then checking the other night where there's supposed to be an event and then seeing it. I mean, that was like, I
Did you
couldn't
know that right then, that you were seeing something amazing, or did you not even believe your eyes?
I definitely saw that there was something in the data that was consistent, I mean, with what we predicted, but I was anxious that I misunderstood the data. And so then we did follow-up observations and we confirmed.
So as a 22-year-old, what'd you do with that data when you saw it?
I ran to talk to my advisor, show him the plot. He's like, and he pulled out a bottle of whiskey and said we should toast to this.
Really?
Oh yeah.
Okay.
I went to his house. It was midnight. I went to his house. Yeah. No, but this was this is your dream, right? You have, you know, now my dream is like I work with students and they bang on the door and there's
And you have a bottle of whiskey handy?
well, no, not me, but but and then I would say when we started the Mirth project and we just turned it on, and very quickly we found one of these small planets, and that blew my mind because when we started Mirth, we had no idea. We thought actually that these M dwarfs would make fewer planets because they were lower mass. So we thought there's less stuff to make planets out of, so you're going to get fewer planets. Nature surprised us. For whatever reason, they're actually better at making planets. But right after we turned it on, I was working with a great student. His name was Zach Berta. He's now a professor at Boulder, okay, coincidentally. But you know, and we found this first signal. And that was very spooky because that planet was twice the size of the Earth.
Mm.
And that is unlike anything in the solar system, right? So in the solar system, we have planets that are the size of the Earth and smaller. And then you jump up to Uranus and Neptune. And there's nothing in the middle. And yet what he found was a planet right in the middle. And we now know that actually that's very, very common, that many of the planets around other stars are actually some kind of planet that doesn't exist in the solar system. It's intermediate between Neptune and the Earth.
A question from the audience that brings us back to the work you've been doing is a very good question. What are the biggest technical challenges in capturing detailed images of exoplanets? How are they being overcome with current or upcoming technology? Talked a little bit about Magellan and some of these other things, but address that.
Yeah, so you know, I would say that the fun part of my job is building things. And so, you know, you have an idea, you want to measure something about the universe, and then you realize, okay, you basically want to trace those set of science ideas into technical requirements. And so you realize, okay, I need a telescope of this size. It has to, you know, like I showed you with the Mirth project, it has to be robotic. It has to work in a mountaintop, whatever it is. And so when it comes to doing the measurements that we're doing, the trick is these are incredibly subtle signals. And so we have to build telescopes that are very, very stable, whether they're in ground or in space. So we're measuring changes in brightness in time. And you can imagine if the telescope heats up a bit, or if the telescope, the focus of the telescope changes a tiny bit. You could introduce things that would look a lot like the signals that you're hoping to measure. And so building facilities that are incredibly stable is novel. And unlike, you know, in business, if you do all this tech investment and you make it work, then what do? You make 1 million of those things or more, and that's how you recoup all that investment. But science isn't that way. We build one special machine. You build one time machine.
Mm-hmm.
You build one telescope like James Webb. And James Webb is the product of more than 1,000 people working really hard, so that we could all build together and build and come together and build one telescope that was going to tell us something profound about the universe. But we're not going to go and build 50 of these things. And so it's a kind of a delightful space to be in, but it's a very different space than what we're used to in industry.
I want to talk with you for a couple of minutes about, we have a lot of good people in the room, but there's also a gorilla in the room, which is funding for all of this.
What?
Right? And, you talk about the James Webb Telescope,
Right.
how long that took, how much that cost. What's the funding picture right now, given what's going on out there? And because obviously a lot of your work and a lot of this other work depends on funding from NASA and other government agencies.
Yeah, right. So I would say that one of the greatest, so I'm an immigrant, okay? I'm from Canada, okay? Thanks. And yeah, well, hey, but, and my mom's a refugee. My mom's a refugee from Eastern Europe, okay? So like, why am I here? Why am I in the, one of the really incredible things that our country, the United States, our country, has done is to have these unbelievably powerhouse research universities where people from all over the world, such as myself and my co-laureate Sarah Seeger, we both went to Harvard, okay? And it's not just about Harvard, it's about 100 great institutions in the US that attract top students from all over the world. And that is held up by federal investment, okay? So you have these academic institutions that are supported by money. In our case, it's National Science Foundation money and NASA, but obviously in other fields, it's the National Institutes of Health, okay, it's the Department of Energy. And why would we ever disassemble that? It would be so foolish to cede that ground, right? So we need we need to absolutely point out that, first of all, the way it's being done is not consistent with the Constitution, okay? The money has been obligated by Congress. It is not for the executive branch to terminate that. But speaking more generally, even as we go into the future budget cycles, like the key part here is, we cannot reduce the National Science Foundation and NASA if we want to maintain this. I mean, there are many reasons. Yes, we are the leaders in terms of space science, but we also are the leaders in terms of a lot of very practical. This is not a practical science. This is a science we all care about. Everybody at some point in their life asks whether we're alone in the universe. And that's what, we're talking about, people are doing research in industries that help the national defense. We're talking about, okay, that's a very practical concern. We're talking about people doing medical research. All of that could go away if we no longer have this model where we, one, welcome students from all over the world and seek to keep them, not throw them away, okay? And put them in vans on the streets of Somerville and things like that. And two, if we don't fund it. So it's something I think a lot about, a lot of my colleagues think about, and we want to make sure that we protect. And we explain to people why this is such a successful model.
So far, NASA is not being hit especially hard so far as we know, right? Where that is right now.
Okay.
What is the status of that and the priorities going forward? Is your work continuing and the funding for your work continuing?
I think one of the real frustrations right now is we don't know what the priorities are in the administration. It just seems so chaotic and so focused on destruction that we just have a hard time knowing. I'm okay with, if we have a national conversation saying we should spend less on space. Like I would disagree with that, but I would be okay with that. But that's not what's going on right now. It's that every day I don't know whether funding is going to be threatened. NASA, my research, no, my research is, and why? Because I also work at an institution that has a large endowment. And so if my money suddenly goes away, we have promised our students they will still be funded. I will still pay my staff. But that's not, a lot of universities don't have that. They're very strong, particularly state schools, very strong academic departments, but they do not have that backstop.
One of the priorities that we do know from this administration is that we want to go to Mars.
Okay, great.
Is that something that we should be spending money on?
am super excited about people going. I love the idea of sending people to Mars.
Do you?
Yes, yeah. I mean, come on. Mars is a planet. Okay, the moon doesn't have an atmosphere. Mars had flowing water. We can see ravines. There is all sorts of exploration to do on Mars. Mars has an atmosphere. The point is, NASA is a fascinating. It's an exploration agency and it's a science agency, and we can walk and chew gum at the same time. We can figure out human exploration of space at the same time that
Even if we're weightless, we can walk and chew gum at the same time.
Even if we're weightless, we can walk. But we can do both. We can put people on Mars on a short time scale. I'm super excited about that. And we can also figure out how to pursue these science questions, like whether planets have atmospheres and whether there's evidence for life, which requires investing in big telescopes. We also need stability. These missions take a decade or more, and we need, and so that's longer than the 4-year increments of different governments. And so we need that kind of continued support. And normally Congress has been very good about basically guaranteeing that, even if the leadership changes, even if the executive changes.
We have some young people in the audience tonight. Raise your hand if you're under 18 years old. If you're younger than 18, raise your hand. There's one over there. Okay, where's the other one? There we go. Raise your hand if you're under 25 years old. Oh, more hands. Okay, we have a picture of you as a young guy.
Oh, you're gonna?
Yeah, let's see that.
All right, he wanted me to show this. Okay.
I wanted him to show you.
Okay, all right.
All right, he's
Okay.
not the guy on the left.
Yeah. Yeah, so I'm the guy in the middle, just to be clear. Okay.
Where did this come from?
Okay.
This interest of yours has been
Yeah.
around since you were how old?
Yeah, so I think, right, so I was the kid, I just cannot remember a time I wasn't fascinated about space. I loved Star Trek.
Is that what got it going, Star Trek, or were you out staring at the sky and Star Trek came along at a good time?
I don't know. I mean, it goes so far, I cannot remember what came first. I remember it was in the 80s, and there was a new technology where you could take a photo and make that your wallpaper instead of it being a pattern. And I begged and begged and begged my parents, and they allowed me, and I picked a photo of the space shuttle, okay? And it was the space shuttle in front of the Earth. And that was just the image that I fell asleep every night looking at this wall-sized picture of that. And so, and yes, as a kid in the Boy Scouts, I would get out of the city and always bring my star chart and try to figure out the constellations. And I remember the first time I could see Andromeda. There's one thing outside of our galaxy that you can see without a telescope. If you're in a dark, you can just see it with your naked eye. And that's the Andromeda galaxy. You can actually just see that without any aid, as long as you get away from the bright city lights. I remember the first time I saw that on a canoe trip, that blew my mind.
And that's when you decided, you read A Brief History of Time, right?
Yeah, no. So no, I was always interested in science. In 1986 there was an expo. Okay, so there were these world expos. So depending on so there were these world.
We used to call it World's Fairs.
World's Fairs
around for a while, right? Remember that?
Right, and so like you would like all the different countries would each have a tent. Okay, and in the tent they would like serve food from the country, or they would talk about the technology that their country was. It was this funny thing that you did really before the internet, I think. To learn about other countries. Anyway, so my family and I traveled out to Vancouver, Canada to go to the expo. And the expo, I don't remember anything from the expo. What I remember is that we went to Vancouver Island. We went to a national park and we camped there for a week. And I spent the entire time exploring tide pools. And I was absolutely certain I wanted to be a marine biologist. I was just passionate about urchins and jellyfish. And I wanted to be a marine biologist basically all through from age 12, from that moment. So I was 11 or 12 then, until high school. And then really at the end of high school, I read this book. That's why I wanted to put this up. And I read, and I realized now I didn't understand it. Like it's the most beautiful poetry, okay? Talking about ideas like general relativity and quantum mechanics, and the fact that your perception of the passage of time and sizes of objects was relative, that wasn't fixed. And these ideas seemed so profound to me that then I pivoted in college and decided to do math and physics instead of biology. but that passion of science, has always been there.
You and I have talked about this too. It's another part of your journey, and it's about passage of time, and that is your health issues that you confront now.
Yeah, so this is going to sound a little heavy, but we did want to talk about this because I think there are lots of people, you might have someone who's going through this as well. So about 2 years ago, I was diagnosed with stage 4 cancer, colon cancer, which has now moved out of the colon in my body. And so that's been a big factor in my life for the last 2 years. But I don't want you to, I'm not like I wish it were not true, but so does everyone who lives to see such things. But I'm not worried about it anymore, and one of the big realizations was like, and I don't want to I'm going to fight this thing, but I think one of the big realizations was like, you might think like, gosh, you suddenly realize like, am I doing what I want to do? Do I need to suddenly change paths, and are there things that I feel I've set aside? And my feeling was like, no, I have married well, I have an amazing
Your wife
family.
is with us here
Yes.
tonight.
And but then on topic for today, like on the professional side, like I think the thing I would do anyway would be to do astronomy and to work with bright students and try to find planets. I think that's still what I would choose, even if I knew I had this all along. So.
We talked about this, and I think it's something that we might wonder about, because we all know that our time is limited. But as you talked about,
Well, I
so
hadn't really
passionately-
thought about that until about 2 years ago.
Well, that's what happens.
And then you really think about it.
So when you're staring, what's so amazing though is, you're staring into the
Yeah.
Billions of years
Yeah.
of planetary expansion
Yes.
history. And so how do those two thought processes mesh,
No,
collide, whatever?
So it's humans have thought about this ever since they realized that the points of light in the night sky were stars. Humans have thought about whether there was planets and whether there was life on those planets. And you can find writings that go back at least fairly specific writings about that idea that go back 600 years. And then more general thoughts about other worlds that we might come into contact with that certainly go back 2,500 years. So we can really see those. So the point is, like, you feel this deep connection. One of the things I love about being a scientist is I write papers, and you often are having a conversation with someone who is no longer alive. Like you're reading their scholarship and you're engaging with their scholarship. And sometime I imagine I will come to an end, hopefully in the far distant future, and people will interact with my ideas, and that chain of, that's this great quest that we're on in astronomy. But there's only one moment where we first find planets, and I was really fortunate to be alive, for all of us to be around when that moment.
You've done amazing things, and you're going to do it for a lot longer. So we're all going to send you very positive energy.
Yes,
Let me go. We have a lot of great questions from the audience, and it's been just such a great pleasure to be here with you this evening. And so we have a few more minutes now, inspired by those who attend. So here's one. If we were to find life on other planets, would we be able to design accurate models of how they function through biomimicry?
Oh, that's a great question. So I think that right now, okay. So if you have a question that you want to answer, you have to think, what is the experiment that allows me to answer that question? And right now the question is there life on other planets? And really embedded in that question, is there life that's similar enough to life on the Earth that I would actually recognize it as life? So that's why we talk about oxygen and photosynthesis. And we think that photosynthesis and water-based life is very reasonable because water is so abundant and light is the natural source of energy. But maybe that's just the myopia of growing up on the Earth. Like maybe there are all sorts of ways to make life that we wouldn't even recognize. So we start with designing experiments to recognize life as we know it. And then you can imagine future generations will come up, or not even next generations, but other people will come up with experiments that I can't conceive of yet that will tell us like whether that life is multicellular, whether it's intelligent, whether there's non-water-based life. I don't know how to ask those questions in terms of things I can measure yet, but 20 years ago, we didn't know how to ask the questions that we're answering now. So the next generation will be smart and will come up with, and it will probably require new and powerful observatories, and that's the chain going forward.
So speaking of new and powerful observer, if you were looking for terrestrial worlds, question here, is it possible to look for blue wavelengths of light? I imagine other watery worlds would also reflect blue light.
Oh yeah, that's a great, there's a wonderful, I mean, long before we found planets, there was a lot of thinking about ways to characterize them. And indeed, one of the ideas is actually looking for the glint of oceans. Like if you're, if you've ever, when you're directly lined up with water and you're backlit from a star, then all of a sudden things get really bright because the water is basically serving as a mirror. And people have exploited that particular idea. That would be at blue wavelengths. And certainly, yes, we could imagine measuring the colors of worlds in the future and directly determining. Actually, we did a really neat experiment. There was an old satellite from NASA, and we repurposed it, and we basically measured the Earth just in its total brightness. So we didn't make a map of the Earth. We pointed the telescope at the Earth, and all we did was measure how bright the Earth was as it rotated in different colors, okay, as the spacecraft was flying through the solar system. And then we inverted that, and we said, could you conclude that there was oceans? Could you conclude there was continents? And when we had a computer-generated map, a reconstructed map of what this fictitious planet was, and you really could see like the correct number of continents and oceans and all that just by seeing like, okay, now blue is really bright, now green is bright, now brown is bright. And so, yes, I think we can definitely do that. Yes.
This isn't a question, but it's moderator's prerogative as I'm listening to you. How
Okay.
does AI change what this is? What's happening here?
Oh, yeah. So, okay. So as a when a lot of machine learning and AI first came out, as a professor, of course, a lot of my colleagues, their first reaction was like, oh, we're screwed because this is going to be a huge tool for cheating. But that's how the World Wide Web was also greeted in its time, and probably how libraries were treated.
How the calculator was treated.
That's right. And people have been able to look up things in books and all that. So that issue aside, no, actually AI has been a very powerful tool for data analysis. It's very good at spotting those ideas. Those computational methods are very good at spotting patterns in data that humans aren't necessarily able to see. And so one of the planets that we found with Mirth was actually, I had a student who was basically doing not necessarily AI, but machine learning, very related idea. And he took a course at Harvard, and at the end he said, the professor said I could use my own data for my final project. And he had an idea, and he went and reanalyzed all the Mirth data, and he found a planet using those methods. And so I think it can be a very powerful tool.
Okay, another question from the audience. Super Earths and sub-Neptunes are the most commonly found planets in our galaxy, but they are missing from our solar system. Could the reason why provide insight into exoplanet habitability?
Yeah, so
You may need to explain a little bit of that.
yeah, who's asking that? Okay, I'm looking at it. Okay, so I think the big message from exoplanets is that nature is far more creative than we were in imagining the diversity of exoplanet systems. So, there are planetary systems that look very much like the solar system, but there are plenty where the fundamental architecture is different. The first planet ever found, this hot Jupiter, people didn't believe it at the time, not because the data were bad, but because the idea was in itself so offensive. People were like, you cannot make a Jupiter so close to a star, and therefore the data must be wrong, which Sherlock Holmes would be very upset about. Okay, so now it is true. So basically, there's all these planets, like I mentioned, this planet that Mirth had found, which was intermediate in size between Neptune's and the Earth. And so when we started finding these worlds, which were 2 or 3 times the size of the Earth, you could either call them sub-Neptunes, because they were smaller than Neptune, which is 4 times the size of the Earth, or more excitingly, you could call them super Earths, which didn't mean anything else, but super Earth sounds more exciting, I think, than sub-Neptune. Now we know that some of them really are super Earths, meaning that they are terrestrial, they are rock and iron, they're just bigger. And others are really subneptunes in that they have an envelope of hydrogen and helium. So we actually know now that both of these exist. Yes, why did the Earth not make them? Or why did the solar system not make them? And why does nature make them elsewhere? I would say there's theory, we really don't know the definitive answer to that. I think that one of the ideas is that in some solar systems, other planetary systems, planet formation happened so quickly that there was still in the protoplanetary disk that had the rock and the iron to make planets, there was still a lot of gas around. And so when you made an Earth-like planet, you also were able to gravitationally capture that gas and make something like a sub-Neptune. And if you do that, that planet's not going to be habitable because it's enveloped in this really thick envelope. It's very interesting for us scientists, but it's not a great abode for life. And so did the Earth, when it was very young, have this temporarily captured nebula of hydrogen or helium or not? We don't think so, but there's some intriguing evidence it might have briefly had one, which has to do with isotopes that we now can see in the crust and so on. So
we have a number of questions. We'll do a couple more quickly, and then we're going to be wrapping up for the evening. This one has got, I see how many votes, some of these questions have. This one has a few. In view of the current state of knowledge, what do you make of the Fermi paradox?
Oh, I love teaching okay, so the Fermi paradox is, where are they? Okay, so Fermi physicists would come up with these sorts of questions, and the idea is, if you had the galaxy has been around so long, and stars have been basically created continuously throughout the lifetime of the galaxy, that even if life was very rare, if one of them or a few of those stars had civilizations and they had any interest at all in expanding, that they would quickly colonize the entire galaxy. And so we should find like derelict spacecraft on the moon, and we should see them flying overhead, and there's nothing to be found. Okay, so that's the Fermi paradox. Now, when I teach that to my students now, I say, where are they all know the answer to the Fermi paradox, which is that civilizations don't last more than a few hundred years in a technologically advanced state. And that's why there's no paradox. And they all know, as 20-year-olds, the answer to that. Why do civilizations, so if you're under 25, what is it that ultimately civilizations do? And the answer is global warming. They discover carbon is a great source, and they pollute the atmospheres, and they cook themselves, and they die, okay? But when I was growing up, there was still a Fermi paradox, and we knew the answer. And the answer was, what was the answer in the 80s? Nuclear weapons. So same answer, like same outcome, but totally different answers, which I think is fascinating. So in terms of the fact that we don't see these spacecraft, that doesn't bother me at all. I mean, maybe the whole idea of wanting to make your presence known and building spacecraft, that's just a very human thing. You could have lots of life in the universe that just doesn't interested in those things.
Okay, so last question from the audience will be the 3 most highly voted on questions that actually are connected. Okay, so here we go. What do you have to say to those who believe there is no life in the universe except on planet Earth? What kind of social upheaval will occur if we find life elsewhere?
Oh yeah, those are
and
great.
How will humanity manage emotionally and spiritually? And finally, if we find life on another world, will we put tariffs on it? Somebody here has a great sense of humor.
Well, yeah. So the answer to the last one is easy, which is that we will threaten tariffs, but then back off when the bond market tanks. So okay. Just
You want me to do those again?
I just want to get it right.
What do you say to those who believe there's no life in the universe except on planet Earth?
Yeah, I just want to get, okay, so the question is not whether there's life elsewhere in the universe. That isn't really a science question because I cannot test that question, okay? There's nothing wrong with it, okay? There's lots of questions that are worth thinking about that we can't empirically test. But the question is not whether there's somewhere in the universe, whether there's life. The question is there life on a planet orbiting out the star that's close enough that I could measure it in some conceivable time frame, like the next 100 years. And that I think it's perfectly reasonable to think that there is no such life, that life is, so I'm actually, like I think many of my colleagues think planets are a natural outcome of star formation, And life, given that the chemistry of planets is not that different from planet to planet, life is a natural outcome of that. And I don't hold to that. I think that that could be the case, but it also could be that life on the Earth was a very rare event, and that within a reasonable volume of space, like 50 light years, even if there's hundreds of stars, all with planets, that we're the only example of life. So that's why it's an interesting science question. If we knew the answer, it wouldn't be interesting to pursue it. But actually, it really could be that, or it could be that we live in the Star Trek universe. The first time you actually have the ability to probe a nearby planet and find life or not, immediately that puts you into two, right? So it could be that life is so robust, it just naturally happens anytime that you have the right chemistry. And we answer that the first time we find a planet and we have the sensitivity to see if it has life or not. You see what I'm saying?
Mm-hmm.
Like right away, you know which path you're on. And then you do the next 10. And if you start to do like 50 and the answer is no, then you know that not that life doesn't exist, but that life is very rare. I think that what's great about this whole field is that it's a science question. It's a science question, but the implications are clearly exceed science. I think it really changes how most people would view themselves and their place in the universe. And that's what astronomy has always done. When we learned that the universe was billions of years old, okay? When we learned the scale of the universe, that put our own physical size and our lifetimes, long lifetimes, I hope, in scale, in perspective. And this is the same thing that we will do when we're looking for life on other planets. It will change how people view themselves. And there's a lot of good writing and thinking about what the implications are of those discoveries. We don't know the outcome, but clearly people will view themselves differently if they know that they're just one of many, many civilizations, or if we find out that to the best of our knowledge, we're really alone.
In either way.
Either way,
If there's life of any kind, it's
Yes.
disruptive on many levels. Right?
I think
that is, as we say, a game changer.
It is a game changer. Yes.
We've talked a lot this evening from your amazing perspective as an astronomer and as a scientist. I'd like you to leave us perhaps as a poet. As
Okay.
people go out tonight, and if we can get to a place where it's dark enough and clear enough to look at the sky, how should we think? What should we reflect on? What do you reflect on?
Well, that's a big that's a big question. So I think that so my wife Margaret is sitting here. Margaret's a physician. She deals in public health, and so it's a very interesting. Our dinner table is very interesting because I think that a lot of our concerns are very immediate, and they're life and death concerns, and they are real concerns with the here and now. I think what astronomy does is offer that kind of cosmic balance to those worries. Okay, and so I think that the profoundly exciting endeavor that we are now engaged in is something that transcends the worries of the moment. I think that it's not unreasonable to feel that every person at some point in their life wonders, are we alone? And that people have thought about that in the generations that preceded us, and that people will wonder about that in the generations that are yet to come. And so, if we choose together, okay, this society, this country, we can choose to go and pursue that question and to build the facilities that are necessary to actually go and answer this question. And there's only one time you get to answer that question, whether we're alone or not. People really, the first time you discover we're not alone. And we can do that now in our lifetimes. And it is such a special privilege to be alive at a moment where that is technologically possible. And that's what I hope people take away, that this is a special time to be alive in terms of really learning about whether or not there's life elsewhere in the universe.
Well, it's been an incredibly special time to spend with you this evening. I would say that in your science, you are a poet, and you've contributed so much, and you've done so much, and we know that you're going to do so much more. So, David Charbonneau, thank you so much for this.
Thank you.
Alan, back to you.
So I think you all know now why David has won the Kavli Prize. I'd also like to make the point that when asked why he could see so far, Isaac Newton has famously said to say it was because he could stand on the shoulders of giants. I think we now know also that the field of exoplanet science is currently standing on the shoulders of David Charbonneau and will continue to stand on those shoulders for some time to come. Before we finish up this evening, we once again want to thank our co-sponsors of this event, the Kavli Foundation, the Norwegian Ministry of Education and Research, and the Norwegian Museum of Science and Letters. Thanks to them.